We should start. It's 4 o'clock now. So our last speaker of this session is my colleague, John Harlim, who is one of the organizers of this wonderful workshop. He got his PhD from University of Maryland in 2006. He joined our department in 2013, and he's now a full professor. He works on a range of problems, including filtering multi-scale dynamical systems, stochastic parameterization, uncertainty quantification, diffusion maps, and non-parametric modeling. He wrote books on data-driven computational methods and filtering complex turbulent systems. His talk today is going to be about machine learning of missing dynamical systems. John, you can start.
All right. So thank you for coming to the last session today. So today I'm going to talk about how to leverage machine learning to do predictions of dynamical systems. So in here, what I'm going to do is I'm going to just start with a simple motivating example. So just consider a Langevin dynamics, which is just a simple prototype model that has many applications, for instance, in molecular dynamics. So the setup here is that suppose you have some known dynamics. So this is the first part. So I highlight this is the known, and the unknown part is the red part, right? So the objective here is basically, given such constraint, let's say if we also have a discrete time series of data of your known component, where I'm going to start calling X the observables, then you want to predict the evolutions of this variable X given some initial conditions, new initial conditions that might not be in your training data set. Okay, so before I go and discuss the method, so first let me point out that this particular problem, which I call it the missing dynamics, has all kind of different names in the literature. It's related to the closure problem. Some people in physics call it subgrid parameterizations, and there are also another sets of literature call it reduced order modeling. And if one has special structure, let's just say if the unknown part is actually has a fast scale or smaller scale, then theory of averaging and homogenizations can be applied in this case. So for the problem that I'm talking about here, I will not assume there's any scale separations. And I personally refrain to call this problem as reduced order modeling because for me, at least, if I call it reduced order, that means I know something bigger to be reduced, right? So that's why I insist on calling it missing dynamical systems, meaning I completely just do not know part of the dynamics. So, quoting this very famous statistician, George Box, essentially it's just say all models are wrong. So in the sense, it's like, I agree with him in some extents, like if you know piece of the dynamics, then basically you are subject to modeling error. But at the same time, I would like to say, like, in the bigger picture, basically the known dynamics can correspond to some first principle. Let's say you can derive equation from thermodynamic law or other type of conservation law. Whereas the other pieces that you don't know. So what I hope to do is actually to embed this with this data driven. So to basically simulate or reconstruct or learn this dynamics from a data driven. So of course, there's a question here like, what if you don't have the data on Y? What you gonna do, right? So this is part of the pieces or building pieces that I want to actually discuss today. Okay. So for these particular problems, I'm just going to show you certain things just to stimulate the conversations. But the whole idea on this talk is that I would like to formulate this problem, this missing dynamical systems problem, into a supervised learning task. And the task is basically to estimate dynamical equations, to predict the unresolved variables. So in this case, so here I'm just showing you one realizations of how to do this using a very simple machine learning technique on a double well potential corresponding to the example that I showed you before. So in this case, you can see basically the true trajectory here as a function of time. So this is trajectory of the x component. It's jumping between the two wells, right? Up and down, and so on. So that's shown by the green curve. And here, the red curve is basically the resulting of an estimator of this unresolved dynamics. And you can see they are actually agreeing up to some path, right? And then they start to disagree, here. So I'm showing you basically simulation of prediction starting at time 0 here. So in the long run, they go up and down, but they start to deviate here. So basically, this is just one, initial conditions, right? So based on this, right, I would like to understand, why, for instance, under what conditions we can guarantee, how long can we predict here, for instance, right? This is showing about 15. So there are many questions, that posed by such example. So first is that how to even mathematically understand this problem using disposable tools such as statistical learning and dynamical systems theory. So how to, for instance, construct a convergence guarantee estimator. So in the sense that, why do I want this? Because then if I can get even an error bound on that, that can tell me, for instance, how many data do I need to, to expect an accurate prediction up to a certain time, for instance, okay? So that's all sort of a question. Can we, estimate the expected lead time in this sense? And also, in the era of machine learning now, is that I want to say how to actually leverage this neural network nonlinear type estimator for, closure problem of high dimensional, which we were not able to do before the explosion of these neural networks in the community. So these are the type of questions I want to address. Okay, so here's outlines of the talk. So first, basically, I will just split it into two. So in the first part is basically I'm going to talk about the data-drivens, but here for the purpose of this audience, I'm just going to remind you the tools. So basically, I'm just going to bring up the language. Okay, what is the connection of Morris-Wansink formalism as one of the idealists, basically one of the idea that has been thrown around how to formulate a closure problem. And I want to make a connection from that with the delay embedding theory from the dynamical systems and statistical regressions. So basically at the end of the first part here is like, what I want to say is like, under a certain choice of projection operator in Morris-Wansink, then I can reformulate this closure problem effectively as a regression problem, regression of minimization problem, okay? And then having that, then you can, start to use any kind of statistical estimation method, in your disposal, whether it's a kernel method, whether it's neural network, whether it's any kind of thing that you want to actually empirically estimate this regression functions. Now, the second part is that once I understand this language, then I'll go back to the closure problem and try to discuss a bit about convergence and numerical example. I'll give you a couple of numerical examples just to entertain you, okay? So that's sort of the plan. So at this point, I'm just gonna not answering the Q&A as well as the chat, because I just want to try to get my message across, and then, but I hope I will answer it later, okay? So, all right. So here's one mathematical formulation of the problem. So let's say we consider a measure preserving ergodic dynamical systems given by this map phi. That map, it's just basically a map on this phase space omega, such that, you have a measure that is invariant under the flow, okay? So now I will define an observable of interest. So X here is basically, I write it in a notation that is similar to random variables. So this is just an observables, okay? So in the previous notation, this X is just that little x that you know, that's something that you observe. So in this case, X is defined such that the little xt is the realizations of X on the state space at time t. But what is the state space of time t? This is just basically X composed with the dynamics being iterated t times on some initial state at time 0, okay? Now, one natural way, because I'm interested to understand the evolutions of this observable X, one natural way to do so is to use or study the Koopman operator, which is basically, an operator that focus on the linear action of the dynamics uh, on function space that describe the observables, despite even the nonlinearity of the dynamics in phi, then we are focused on linear operator. So in this particular way, the Koopman operator iterate t times here on any function f in this L2 is just defined as a compositions of the observables with the dynamics iterate t times. So in this case, what we are interested here, this quantity of xt here, can be written as a Koopman operator acting on this observable at time 0, iterate t times, okay? Now, in order to build up the theory of Morris-Wansink, basically, now let me define a orthogonal projection operator into a range space of V here. What is this V? It's just basically, V is just collection of this subspace of L2 function here that can be written as a function of X, okay? So now, given all of these tools, we can start to define the Morris-Wansink. So the Morris-Wansink is basically just you apply the Dyson formula to represent the Koopman operator. So here's the Koopman operator acting on observable X, evaluated at a particular state. Then you can decompose this Koopman operator into 3 particular terms. Here, the first one is the Markovian term, and this is the memory or non-Markovian terms. And here's the remaining term, which is the orthogonal dynamics, because this is orthogonal to the subspace of V here, okay? So basically, there are many works has been done in this community, okay? So, but let me, point out one of the things that I want to highlight is that this representation is not unique, okay? Because it depends on the choice of the projection operator, okay? So for example here, so here I'm just taking some example from paper of Chorin, Halt, and Kupferman. It's like one can choose P to be conditional expectations of given observables. One can also choose to be, like linear projection, like this is basically sometimes also referred as the Mori projections. So there's non-unique way on how to do this. Basically, if one choose, for instance, the conditional expectation, then one might have a very difficult representation of the non-Markovian terms, okay? If one choose this linear projection, then you have a simple Markovian and non-Markovian, but then the orthogonal dynamics error could be pretty large. So there are lots of works is being done on this and written up to this point. Now, what I want to do is I will not actually choose either of this projection type of operator, but instead I will basically motivate the choice of P using the so-called delay embedding from the theory of dynamical systems. So first, let me define what is a delay coordinate map. It's basically a map. You take the state space and map it into like observables. So here's the definition. It's like observables at the previous time. So this is delay embedding. So here's my observable at current time minus 1 step, so on. Okay. So the delay embedding theory. So here's there are many versions apparently, and one of it is by Tim Sauer, York, and Kasdagli, and another is sometimes we refer it as Taken's embedding theory. So under some mild assumption on X and the flow map, so this theory is basically states like if you choose this M here large enough, then basically this map here, this delay embedding map here, is a homeomorphism between the support of M and the invariant and this range Rn. Okay. So what this really means is that the following. This means like the Borel sigma algebra of this support of M here is identical to the sigma algebra generated by this delay embedding map, which means that if you take conditional expectations of any function conditioned to, this delay embedding, this means like there's nothing more hidden. It's like you know everything, right? Under the random variable. So this is just basically equal to an identity map in a sense, like there's nothing random anymore. So that's basically the essence of this. But regardless, I'm going to choose this. I'm going to choose the projection operator to be this particular conditional expectations. Now, with this choice, okay, so here's my choice. So I choose P to be, I call it now PM, okay, for large enough M such that the theory of delay embedding holds, okay. So if I choose this, now the Q, which is I minus P, this is completely zero. So that means with this choice, effectively, I am killing the non-Markovian and the orthogonal term. So my dynamics is just simple because it's identity map in this case, right? But now if I look at this, basically this PM is conditional expectations of, one iterate in time, conditioned to what you know before. Although this is an identity operator, but in terms of a dependence on these covariate variables here, X, all of this X, this is very non-trivial. And in fact, this is just the flow map generated by the delay embedding coordinate. So by looking at this function as a conditional expectation, this basically shed a light, then this must be a regression functions of an appropriate minimization problem, right? So in fact, one can estimate this regression function by solving a supervised learning problem. So let me write this M0 again, which is this functions. This is a minimization. So this is a regression function of a minimization function problem that is trying to find a map that takes this delay embedding coordinate as the covariate data into the xt plus 1, which is your response. Okay. So here's sort of the detail, what is the class of space that you're looking for. Okay. So this connection now, right, basically just saying one thing, right? You look at Morris-Swansky equation. If I pick my P to be super trivial, I just say the delay embedding coordinate, and this connection to conditional expectation just tells me like, hey, this is basically the function that you're looking for, that you should be formulated or look at it from the perspective of supervised learning. So once you have this connection, that means now you can basically solve this problem using any supervised learning algorithm that you have in your disposal. So here I'm just going to give you one example to do so. So in this case, particularly, I'm going to try to use this following method based on the diffusion maps. So basically the idea is the following, okay? So if you have functions, right? Then this function can be approximated by this integral, which we call just smoothing over a Markov kernel, where a Markov kernel here is constructed basically using the diffusion maps algebra, okay? So if you do this, right, basically it's a very simple method. Then what we can say is just the following. First, we can also estimate what's the error bound on this, okay? So suppose if Q is defined the density of the sampling density, okay, defined under the condition is absolutely continuous with respect to the volume measure of the manifold. So here's, I'm assuming there's a manifold, the data lies close on the manifold. then basically one can approximate this the error estimates on discretizing this integral operator. So pointwise here, basically, you have an error estimate from the integral or the continuous approximation. So this is just error estimate of approximating Q because you don't know what is the density. And the third part is just the bias due to the discrete estimator. So these are basically just the estimate that I had with the older, with Harris-Berry on the older work that is actually unrelevant to this. But now we're just applying this method, to approximate this function M0. So in this case, right, numerically, this is very easy to do. As soon as you construct this kernel, right, then what you do in order to make a prediction now or to use to estimate M0, evaluate at new data, you basically just, pair up with the new data with the training data point, and then you just multiply with the training data factor M0. That gives you the new predictions. Basically, that's how it is. Now, I will say, like, all this method, this linear estimator like this, they all subject to curse of dimension. Okay. Now, I want to show you one particular example just to illustrate you a couple of things. Why this such formulation is actually. I want to make a point like this formulation is actually interesting. So here I'm just testing a purely data-driven modeling. So in this case, I just pick a very simple dynamical systems introduced by Lorentz. So this is not the Lorentz butterfly that you see in many cover of magazines. So this model basically is just an ODE. You see here, I'm just putting like 5-dimensional ODE. The quadratic term here is basically conserve some energy, and this is just damping and some forcing. Okay. So what I'm showing, the problem here is purely data-driven in the sense like I'm going to just tell you a time series of omega-1. So basically the observable is just one component of this, okay? And I'm going to basically, estimate the evolutions of this omega-1 under this delay embedding coordinate. So what I show you on the left here is just a trajectory of the truth, which is the black one. So here I show you, let's say we start from initial condition 0 at this point. So you will show the estimate of the prediction estimate, as you increase the memory, so or the M here, then you're approaching the true trajectory, okay, using this kernel smoothing method. And on the right is basically, you can ignore this dash using the Nystrom, which I don't have the time to discuss here. But you can see actually this is sort of error measure out of 10,000 verification samples. So whatever on the left is just one typical predictions path, and whatever on the right is a more statistical that we average it over 10,000 verification samples. Okay, you can see that as M is increases, then the error is going down. Okay, so basically, I want to conclude the first part just saying like, what do we learn here? Is like the delay embedding, right, simplifies the MZ equations to Tarkan's flow map, right? So M0 is nothing but the Tarkan's flow map. So this is just trivial statement. And the conditional expectation, however, the conditional expectation representations of this map here allows one to basically access it as a supervised learning task. And this is basically the key, okay? So now having this in mind, basically I want to just go back to the closure problem, right? So I want to go back to the problem that we talked about from in the beginning of the talk, okay? So now here's the missing dynamics problem. Let me remind you, basically here I just denote X as the resolved or known resolved variable and Y is unresolved variable. And assume they satisfy this just discrete map in this case. The task here is just to reconstruct an approximate dynamics that can track xt, and in some case even the invariant statistical distribution of x. Okay, so in this case, first, to understand, how to reformulate this unknown dynamics using all of the language in the previous sections, let's start with the simple case where time series of X and Y are given. Of course, in real application, Y will be very high dimensional and you won't be able to actually have an access to that. So in that case, we will consider the case 2. Basically, you don't get access to Y, but given only X, you actually can identify a latent variable theta that directly affect the known dynamics. So I will explain that with example in more detail later. Okay, so let's start with something simple. So here, this is just 2 dimensions. So let me track the time. So I have 20 minutes. Now, let me consider like the full dynamics is just 2 dimension in this case, right? Euler-Maruyama discretizations of a system of SDEs. So it's very simple. So this is just white noise here. Okay, so this is just Euler discretizations ODE. Now, what I don't know is this red stuff. So I don't know the G, I don't know sigma. Okay, so the notations following the procedure that I prescribed in the previous discussions. So the procedure here is that I would like to rewrite this unknown as a conditional expectation. Basically, just as simple as that. Okay. So let me rewrite the target function here as follows. So this is just expectations of the finite difference approximation of the derivative of the y given x and y. So instead of keep spelling this out all over, I'm just going to make the notation simple. So this is just that. Okay. So with this notation, so let me replace. So I'm replacing it here. So that's my target function now, is that G. Okay. Now, let the same thing, except now I have a script epsilon denotes an estimator for G. So this is just, the epsilon will characterize the error of this estimator. Okay. So now once you estimate this G, basically what happened here is that you can also use the residual of your training of G to define an estimator for the noise amplitude. Okay, so this is just standard procedure. Okay, now you have this in your hand. Basically, here's what I can say. So now consider, here's my approximate model. So this is known. So this is my approximate model. So now I replace this with, here's my estimator, the one that has epsilon, and the hat. These are 2 estimator. Okay, so here's what I can say is actually, if this is a consistent estimator, meaning my estimator will converges to the target functions, okay, with variance error of order epsilon square. So this epsilon is basically, we will call it, let's call it the learning rate. So basically this is depend on what estimator you're using, right? Then under the condition that if F and G are Lipschitz continuous, and given the same initial conditions, then you can show a strong pathwise convergence of order time, polynomial time t squared. Okay, so what is interesting here, the first time when I see this is like I said, well, if you really want to get an accurate prediction, then this is what you expect, right? You expect, this is basically depending on your learning rate, inversely proportional to your learning rate to the -1/2, right? So then it just depends on what kind of method that you're using to estimate this. That will tell you maybe the relationship between how long of a path you expect to have an accurate prediction to the length of the data that needed, right? So okay, so let's go back to that simple example. So here again, remind you, this is known, this is unknown. So we learn this completely from the data. I'm just employing a very simple kernel embedding technique. So effectively, this is at the end, this is just, I would say, embarrassingly, it's just polynomial chaos expansion because this is just 1-dimensional problem. Okay, so here, in the left hand side, so I'm showing you, which is the same figure that I show you in the first slide, is like the trajectory when I, the discrepancy between the estimate and the truth, okay, basically using 50,000 data to train. On the right-hand side, I use 500,000 data to train. Okay, this is just two-dimensional problem, okay? Now, if I, use the minimax, because this is a linear estimator, this is just basically linear estimator. So if I use the minimax error estimate, basically, which, is famous in statistics by Stone, 1982, says like, if the function class that you're trying to estimate are in the Sobolev class with smoothness beta, then the variance bias trade-off is given by this error rate. So let me be very generous. Let's just say beta is just infinity. In this case, it's quite nice. Dimension is only 1, right? So that basically saying the time you're going to get expected to get an accurate prediction on the left is probably about 15. On the right, it's about 26. This is super conservative, right? So I'm by no means I'm claiming this is a good estimate, but this is just opening an umbrella between like, how do you, kind of justify, oh, this is actually going to work, right? This pathwise is going to work up to some times, okay? So that's one. So now let's, I will also show you what is the long-term statistical approximations. So in this case, I'm trying to predict the bimodal distribution. So you can see if you use more data, then you'll catch the bimodality. And also here's the autocorrelation functions. And here's another statistics people kind of use to basically quantify the mean exit time and the reaction rate between the full model and closure model here. So in all of this metric, you can see if you use more data, you basically kind of get a better approximation, okay? Although at this point, I do not have this is in the working, it's like we are working on the theory of how to justify this, how, and also the correlation functions. So now let me move on to a more realistic situations. Okay, so in realistic situation, as I said before, right, you don't get to see why. Why is the unknown dynamics. Okay, and this why, even if you get to see it, it could be really, really high dimensions, and you do not want to construct a surrogate model of that. Okay, so instead, I sort of define what I call is unresolved, identifiable unresolved variable. So what is this? It's actually the following. If you write the dynamics, f as function of x and y, but I want to identify it as a function of resolved component and some other unresolved variable, but which I can identify. So this theta could be, some function of xi and yi. So let me just, instead of keep elaborating, let me just give you an example. Okay. So here, for instance, here's a Galerkin Fourier truncation of just cubic NLS equation. Okay. So this is UK is the kth Fourier mode of this Fourier Galerkin truncations. Okay. So now suppose, okay, the resolved variable here is just the 0th mode. So I'm interested only on the 0th mode, right? So if this is 0, k is 0, so I don't have a cubic term. So you just replace all of this with k equal to 0. So the equation is essentially just this guy, right? But if you look at this, I can rewrite it as equation that involve only the resolved component and a lot of other things on the unresolved modes. So basically, this is what I call the identifiable unresolved components. Effectively, what I'm saying is like, look, if I just give you a time series of U0, you cannot recover, you cannot identify all of these higher order wave, Fourier wave numbers, but at least you can recover theta, which matters, right? Which is, pretty much effectively act as a forcing to the first component that you're interested in, okay? So this is the theta. So here's, I hope this clarify what I mean by identifiable unresolved variables. Okay, so now, okay, suppose, I want to rewrite my full dynamics now. Okay, first the x is basically f tilde as a function of x and theta. Now the theta here, right? This is the observable. So this is now the new observables. So I would like to write this, so here I take the liberty to use the notation of Morris-Wansink, which is just very simple, right? In terms of conditional expectations of random variable theta, t plus 1, conditioned to this delay embedded coordinate of z, which is defined as x and theta. Okay, so that's as simple as that. So basically here, this is nothing more than rewriting the full dynamics in terms of x and theta. Okay, the full dynamics, remember, it was in terms of x and y. Okay, so now if you consider an approximate model like this, so here my estimator again with epsilon. Here's some residual. I'm just adding some error on the residual. Okay, now if this estimator is also consistent, with variance order epsilon square, and eta here is a Gaussian noise with variance that can be estimated from the data, then here's what we can say. If this projection operator is uniformly bounded, so basically what this means is really that these functions here, g, okay, f and g here, I mean, g is basically Lipschitz, uniformly Lipschitz with respect to x and theta, then you can estimate the following error bound. Now, right, this error bound is not that promising because now basically this is exponential to t, right? Well, first of all, I don't have any more structure in this case, right? Besides these functions. So we don't assume a lot. And the second thing is like the proof here is just super trivial. You basically flip the page on the old classical ODE, which says like, under perturbations of, if you perturb the vector field, then, the solutions, will be pathwise converged using sort of like Gronwall type argument. Okay. So now, I'm sure if I consult with some expert in the chaotic dynamical systems, they'll tell me this A got to be related to Lyapunov exponents. But at this point, I haven't consulted anyone yet, or haven't got anyone excited to want to talk to me about that yet. Okay. But okay. So now we have this, at least this is just saying it's just consistent so long as if you have a consistent estimator, then you can get pathwise prediction, but it doesn't tell you how long, okay? So here, I'm going to consider a neural network estimator, okay? So basically the idea is that I want to estimate this guy, right? This conditional expectation. Remember, I want to estimate this guy. So as I said, now you can use any estimator you want, okay? So I'm using now a particular a type of recurrent neural network called the long short-term memory. So just for a notation, so this is the neural network. Here, W denotes just the parameters. So I do not want to discuss much about this because I'm probably the least expert on LSTM. But in the back of my mind is basically you're solving this minimization problem, okay? You train this minimization problem using this LSTM network. A lot of people has used this, but so we tried. And basically, the other thing that I also want to acknowledge is actually, I did not do this numeric. So all of my collaborators do this. So I should give them the acknowledgement. This is Haichao Yang and his student Sun Wei Liang, and also my former postdoc Xixiao Jiang. So they all responsible for this numerical result that I'm going to show you. Okay, so we try this on Kuramoto-Sivacinski equations. So basically, the Kuramoto-Sivacinski equation here is defined as such in the periodic domain. Here, Vk, it just denotes the kth Fourier mode. We set this the length of the domain, so that it has like 3 unstable low modes. Okay, so numerically, what we did, the experiment is as follows. Okay, so this is minute 40. So I have 5 minutes to wrap this up. So numerically, the true trajectory is constructed using 48 modes. Okay, we will resolve only 6 modes. So this is resolution of the 6 modes. And you can see this is my theta. This is my identifiable unresolved variable. So I use the LSTM to learn these conditional expectations. Okay. When we start looking at this problem, we say, wait a minute, this is a 480 dimensional problem. How come, right? This is 6 Fourier modes. So each of this is 6. So 6 times 2, that's 12. And then you have memory length M. We put 20 of M. So 12 times 20, that's 240. But then this is complex value. So that there you go, 480 dimensional function approximation problem. So basically, this is what we can show. Here's the spatiotemporal of X, comparing, this is just the error in this case, as a function of time between the true dynamics and the predicted dynamics using this closure framework. And here's just, some diagnostics. So we compare, if you just completely ignore this evolution of theta, so we call that bare truncations, and you compare it with using this correction, this closure correction. So you get a better performance in terms of statistics. So this is just a snapshot out of the statistics that RMSE is just over 1,000 out of sampling initial conditions. And then here is more detail of like evolution of the spatiotemporal of the truth. So time goes up, spatial, horizontal. So one of this is the truth, the other is the estimate. And here's more closer look of prediction of one of the Fourier modes here. So this is the trajectory of, let's see, Fourier mode C. I don't know which Fourier mode is this, but one of them. Here's also autocorrelation function. You can reconstruct the energy spectrum of the 6 Fourier modes and cross correlation and so on. Okay. So what do I got here? I have 3 minutes. So, okay, let me entertain you with a couple things. Now, this is combining, known dynamics with data-driven. So one of the other questions when I start this project is like, I want to understand, like, can we now actually understand the success of many, many proposed parametric type modeling, right? So here's my attempt on this. So one way to look at this is basically to look at the RKHS formulations. So remember that what I want to estimate is this guy, this conditional expectation, right? If I use the theory of kernel embedding, right? Basically, if I pretend that this functional that I'm interested to estimate basically live in an RKHS, a particular RKHS, then I can basically write it down as a linear span of the features in the RKHS. So here, particularly if I choose my feature to be orthonormal under some L2 space, then I can get the RKHS induced subsets of this L2 space. So this is actually the first time when we think about this, is basically using this RKHS theory. Now, why do I think about this, right? So the idea is that, well, if what we do is you can never actually represent this using infinite summation, right? But what we always do is we represent using finite summation, right? And as soon as you make a truncation, you actually going from a non-parametric problem, which means you have infinite parameter to estimate, into a finite, into parametric problem, right? That you have a finite number of parameters to estimate. So then at the same time, this is basically just going in the reverse direction of kernel tricks, because kernel tricks saying, well, it's maybe better to use a kernels like as an inner product of two features. But here, what I'm not suggesting to do this, but I'm just suggesting try to understand the parametric modeling of paradigm. It's just, okay, if we go back to this, then you go back into the parametric. So what I want to say is basically just the following, right? The second point here, I guess, is probably more important, is like we turn basically this missing learning dynamics problem into basically just specifying this basis. So if you want to use an orthogonal basis, right? I mean, of course, if I'm being really stupid, like what Chris Swab was saying earlier, you choose a monomial x squared, x cubic. That's usually how we put the model, but that's being pretty stupid, right? Maybe you want to be more clever, right? Using like orthonormal polynomials. So that's another representations. But you know, so basically my point is like, it just depends on the class of functions. So if you choose this to be, you know, up to order m, then you are saying, okay, I'm going to approximate my process or this missing dynamics with a class of function belong to this orthogonal polynomials of degree m, for instance, you know. So that's what's the main point in this case. Now, for example, right, one can also use this principle proper ordered decompositions basis, right? In that case, you end up with just linear approximation. So, okay, so I think I'm running out of time, so I'm not going to dive in, although I have examples on other things, but I don't want to take more time because it looks like there are 22 questions. It's scary. So the conclusion here is that we develop a closure modeling framework and just systematically identify the target functions. And then I do not want to advocate one particular estimator against another. You can use anything you want in your disposal. What we did is we just reformulate this as a supervised learning so that at least you know what the target function is. So if you're interested, basically the first part of the talk is here. It's going to appear in Physics D. The second part is in this paper and about the, you know, the third part, which I didn't quite say much on the RKHS formulation, is published in this paper with Xixiao Jiang. And if you're interested to learn more about RKHS induced by the L2 inner product, even in non-compact space, then we have a paper, in fact, a poster later. He Chang is going to talk about that. And if you're interested with the diffusion maps that I talked about earlier, this is a much earlier paper in 2016. So I'll stop here. Thank you very much for your attention.
Thank you, John. Are there questions? So there were some questions from the chat box, but I think that was an overflow from the previous talk.
I see. Yeah. It actually kind of scares me. I look at it 24. Okay. I'm like, oof.
Right. Are there questions from the participants? If you have questions, you can write them in the chat box or Q&A. Are there questions from the panelists? So have you tried on any transient problems?
Meaning time dependent?
Not just
non-autonomous, you mean?
No, meaning that the solution is not a stationary process yet. It's not reaching equilibrium yet.
So, you know, in that case, I'm actually a little bit worried at how do you do the Monte Carlo, right? I mean, because I need to do training, right? Mm-hmm. So all this training is actually based on samples of time series, right? Yeah. So that's, I don't know how to say about that. Mm-hmm. I never thought about that. Okay. That's probably a very tough question.
All right. Other questions?
Can you, John, I do not know much about this subject. This Morse-Swanson formulation and machine learning, what's the relationship? I'm sorry, I don't quite get it.
So what I want to point out is like people usually try to decompose actions of dynamical systems, right? So you here, this is just an operator that tells you how your observables is actually evolving, okay? So one can represent this using Morris Wansik, right?
Yeah.
Now, the object is that, the problem here is that when you try to represent this, you have flexible choice of projection operator, P, okay? Now, depending on how you choose the P, this guy, the Markovian or the non-Markovian, that could be completely complicated, expressions, right? So there are many approximations. For instance, I think Xiantao is advocating, for instance, using this rational approximation to approximate non-Markovian term, right? So you can approximate this term one by one. So then you see, like, the problem is approximation this operator. So that's probably the one simple way how to tell you the connection to machine learning, right? So what I did is basically I'm just rewriting these guys, as a supervised learning problem. So basically the key is basically, I would say, where is it, like this particular slides, right?
You would learn the projection or?
Huh? I'm not learning the projection, but I'm learning a function or a dynamics that maps, the projected variables from the past to the future.
What is the training data you use?
In this case, it's just the training data, which is the observables, which is the low dimensional observables in the past. Oh, that's the training data, it's just X.
Okay.
Right.
All right, so there are a number of questions from the Q&A and the chat box. The first one that came up is, do you need to specify the memory form in the LSTM?
No, this is the beauty of it. It's actually completely no. Because what we were doing was just saying, like, look, this is, by putting more memory, by adding more delay embedding here, right? Then your Morris-Wansik becomes simple, right? It's simplified because this is gone, that is gone, because of the fact that they have this Q term, right? So the Q is orthogonal. So once you simplify it, you only have essentially your Morris-Wansik become just a super trivial Morris-Wansik. It's just there's contribution is only on Markovian in quotation, right? But it's actually a non-Markovian functions of the time of the memory, right? So this is what you want to learn, right? So what you do in your LSTM is basically, you just put your covariate data to be this time series in the past, and you predict, the time series in the future.
So the second question that came up is, could you please explain again how orthogonal terms turn into zero? I think it was in the first paper.
In the first paper, yes. So basically, I think this is the key here, right? So if you under the delay embedding theory, okay. So this map is homeomorphism. Okay, what does that mean is that the Borel sigma algebra generated by this, support of the state, under the invariant measure is essentially equal to the sigma algebra generated by this delay embedding map, okay, or delay coordinate map. So what does that means is, like, this conditional expectation is just identity. Look, if I plug in anything here, it just come out. So that means is, like, you condition to, everything about the secret of this random variable, right? So if I choose that as my P, right? Basically, that means if I apply Q on any, UX here, so what is Q? Q is defined as identity minus P, but P is identity operator, so that's cancel. So that's why anything that you have Q, this is cancel, and that's also cancel, and it simplify the problem. Basically, I'm just restating this, right? That's.
Yeah, the next question is there a systematic way of estimating the best length of the embedding?
The best length of the embedding. That I do not know, actually, because in experience throughout our, at least empirical experience, right? what we experience is the following. There are some systems where probably even, if you given a finite amount of data, right? And this delay embedding prediction is actually saturated. It cannot give you anything better than it doesn't give you a good prediction. But that could be also another thing, right? It's like, it could be, how do you actually approximate this? Because this could be a very high dimension, right? And to be honest, like, before even last year, I wasn't actually quite sure how this will work, because if this is like high dimension, this is M is 20, I mean, how do you actually approximate a 20-dimensional function? I didn't even know at the time. And then this is why when I start talking to Hai Chao Yang, he say, let's do neural network. And then, I just pessimistically, I don't know what to expect. And then they just show me all this beautiful result and I get excited. Oh, you can do 480 dimension. So that's sort of.
All right. Other questions? If not, thank you, John, for the nice talk. I'm going to give the floor to the organizers, and they probably have closing remarks.